Welcome to Code Disclosed. In this video, I will go over the idea of curve fitting and least squares regression. So the idea is I will present a very brief introduction of the math behind the curve fitting, and then I will show you how to implement this in MATLAB and what are the right commands to use to implement this in MATLAB. So first, let's start with the idea of regression. So if we have a bunch of data points, for example, I want to best fit this data points with a model, for example, line or a second order polynomial or any other curve. But I want to best fit this data points with a curve. And this is the idea of regression. The idea of regression or a curve fitting is to best fit a model to some data points using optimized parameters. So here we have two key points, words we need to point out, which is best fit the model. What do we mean by best? And here we have optimized parameters. So how can we calculate these optimized parameters? All right, we'll figure out in a minute. So finding these optimized parameters that best represent the model, in our case here is the line, so the model is the line, requires an error metric. If we manage to calculate this error and minimize this error across all data points, then we can say that, all right, the model that I've picked is the best fit for my points or for the data points that I have. All right, the question here is what kind of error metrics that we could use and how we minimize this error. All right, let's start first by listing a couple of error metrics that are usually used in such topics. So, for example, here I have a bunch of data points: x, y1, y1, x2, y2, and xn, yn, which are the red points. And I want to fit a curve, in this case a line, which is ax plus b, through all of this data. And I want to best fit this line. The magenta here, or the purple lines here, are the error, which is the distance between each red point with the best fit line I have. So this is the best fit line or the best fit model, and these are the points, and these are the errors between each point and the line. First kind of error that we could use, we call it maximum error, or E infinity, which is the maximum. I need to take the maximum of the distances between each of these points and the line, and then minimize it. So I can know at which position I need to put this line in. The second kind of error is the average error, or we call it L1 error. So in this error, I need to take the distances between each of these points and the line, and then sum all of these distances, and then divide by the number of the points. So basically, I'm calculating the average error, and we call it L1 error in some other applications. The third kind of error is the root mean square error, or what we call it L2 error. In this error, I sum these distances, but instead of summing only the distances, we sum the square of the distances, and then we divide by n, the number of the points, and then we take the root, the square root of this value, and we call it root mean square error, or L2 error. All right, now usually the third kind of error, which is the L2 error, is the standard type of error that is usually used in software and we usually use. But there are other applications that L1 error is much more useful than the L2 error. The maximum error is not that much used because it's not very helpful when you have like an outlier up here or down there. If you have an outlier point, then this maximum error will make this line a bit skewed to the outlier. It doesn't give you the best fit line according to the whole bunch of points. So we are going to just focus on the root mean square error for now. So I want to minimize this. All right, so the idea now is to minimize this error in order to get the optimized parameters of this line, which is A and B in this case. Okay, if I want to minimize all of this, then I can say I can optimize just this bit of the error, just for simplicity actually. I'm going to call it epsilon 2. So epsilon 2 is just the sum of the squared of all the distances between each data point and the line. Now fx here, fxk, is ax k plus b, which is the line, minus y of k. Y of k is the y's of each of these points. Now, the idea here is to minimize. Now, from calculus, we know that if we want to optimize something, we need to take the derivative of this something and then set it to 0. So if I want to get the minimum or to minimize this error in order to get the coefficients of A and B, or the optimized A and B, I need to take the derivative of epsilon 2 here with respect to A and set it to 0, and then take the derivative of epsilon 2 with respect to B and set it to 0. In this case, by calculating this, these two equations, I can get to the optimized A and B, and hence the optimized position of the fit line, or the best fit line. All right. Let's do a very rough calculation here. So this is my epsilon 2, and I want to take the derivative with respect to A and set it to 0. So this is the, I just take the 2 and take the derivative of the inside the absolute value here, and then divide times x of k, which is the derivative of a x of k. This is the only one I take the derivative of, because the rest is not dependent of a. Let's expand this. So you can see here the 2 goes away because 2 cannot equals to 0. Only the 1 in inside if you expand and put it to 0. So this is the derivative of epsilon 2 with respect to a equals 0. All right, let's do exactly the same, but now with b. If I take the derivative with respect to b here, so the derivative with respect to b here is just 1. This term is the only one depends on b. So this is the derivative of b, and that's 2 divided times all of this bracket. Now, also 2 here cannot equal to 1 to 0, and 1 cannot equal to 0. So we end up only with this this bracket equals to 0, and this is the derivative of epsilon 2 with respect to b. If we look at these two equations, actually, you can see that these are 2 by 2 system of equations. You have 2 equations, you have 2 unknowns. By solving these 2 equations, you can easily get the values of A and B, the optimized values of A and B, that will give us the least square fit line in this case. All right. Now, sometimes the points are not like this. Sometimes the points are just like this. You can't. It's best not to fit a line through these data points. Maybe it's best to fit a curve or a second order polynomial of the form of ax squared plus bx plus c. So fitting a line here won't give us a very good model. Sometimes we would like to fit a curve through this. In this case, if we want to apply the roots mean square error here, so the fxk here, it's not a line now, it's ax squared x of k, bx of k plus c minus y of k. Now, it's exactly the same thing here. I need to minimize this in order to get the optimized parameters a, b, and c. So this curve would be optimizedly positioned. I need to minimize. It means that I need to take the derivative of epsilon 2 with respect to a, set it to 0, with respect to b, set it to 0, with respect to c, and set it to 0. And you can see here, instead of getting 2 by 2 system of equations as in the line, here I will get 3 by 3 system of equations. Solving these system of equations, 3 equations, 3 unknowns, I can get a, b, and c, and then I can know at which position I need to draw this curve. All right. Now the question is how to code this in MATLAB, whether it's a line or it's a curve. So let's move to MATLAB here. And let's now I have prepared two set of data sets here. So the first data set is just a line data set, and if we choose a line model, it would be best. And for the second data set, if we choose a curve or a second order polynomial, it would be best fit. All right, let's start with the first one, and then we can go through the second one in a minute. Let's first try to plot it just to see how it looks like. So let's go for black ones, black circles for the first one, and let's see how it looks like, the data points. Oh, sorry, it's not x here, it's x of 1 and y of 1. Okay. So let's see how they look like. All right, so this is my data points. These are my data points. On the x-axis you have x, and on the y-axis you have y. And I want to, and you can see here that it's best to choose a line that goes through all of this data. All right, now what are the commands that we need to use in MATLAB in order to use the least square error and minimize it and get the optimized parameters A and B in order to find out the best fit line. Now, first of all, I have the polyfit command. So polyfit command, the polyfit command calculates for you the optimized parameters A and B in case of a line, that will minimize the error, minimize the root mean square error, which is the L2 error. Now the arguments here, I have to enter x and y, which are the data points, and there is a third argument. Now this argument shows you the degree of the polynomial fit. So for example, if it's 1, then it's a line. If it's 2, then it's a second order polynomial. If it's 3, third order polynomial, and so on and so forth. Now, because I want to fit a line through the data points I have, then I will put 1 here. All right, let's call this the coefficient 1 equals to the polyfit of x and y for a line 1. In this case here, so here it will calculate the coefficients A and B for the line that goes through all the points X and Y. All right, now I want to evaluate, so I have AB, the optimized parameters A and B, but I need now to draw this line. To draw this line, I need a vector, another vector that allows me to evaluate A and B, or evaluate Y at each of this vector, at each of this vector points. I will call this vector xp, and this vector goes from 0, and the steps is 0.1 and ends up at 7. And now I want to calculate y of b, which is polyval now. So polyval here evaluates this line using the generated coefficients A and B as before. Okay, values of x must be chosen as we chose it here from 0 to 7. So polyval here, I'm gonna go through the coefficients, and then so the coefficients 1, sorry, and then I need to evaluate at all of these points of x and b. All right, let me hold on here because I need to plot the best fit line on the same plot. So plot xp and yp, and let's use it as blue now. Let's run this and see how x, again, that's x of 1, y of 1. Okay, let's run this again and see All right, so you can see here the black dots here are my data points, and the red line here is the best, the least squares best fit line, which means that the coefficients of this line are calculated by minimizing the mean squares error, or the L2 error. All right, so it's the built-in algorithm in MATLAB. While when using the polyfit command uses the mean square error, or minimizes the mean square error in order to get you the optimized parameters of the model that you have picked. All right, now good. What if I have, for example, another set of data, x2, y2, and let's show these data points. So x2, y2. Let's use the red circles now, and let's see what they look like. All right, so you can see, so this is the second set of data, if you can see here, and you can see that this data is going like increasing in a non-linear way. Okay, it's a non-linear dynamics of this data. So choosing a line go through this data is not a very good choice. Maybe a second order polynomial would be a better choice. How to do this? Well, we need to go through exactly the same steps as before. So here we need to calculate the coefficients now for the model. But the model that I'm picking here, or I'm choosing here, is a second order polynomial. So I'm going to go for polyfit, so fit a model for x2 and y2. These are my data points, but now I need to choose the degree of the polynomial fit to be 2, not 1. So I don't want a line, I want a second order polynomial. In this line of code, polyfit will calculate A, B, and C. So these are the optimized parameters of this curve. All right, let's do exactly the same thing. I need to evaluate this curve on a new set of points, which is from 0, 0.1 until 7. It's exactly the same as before, so this is not O, this is 0. And let's calculate here the new y of p. So let's, I don't know, let's go for y of p, okay, 2 equals to polyval of coefficients 2 and x of p. And then let's, okay, now here let's do a hold on so we can see the curve. So plot xp and then yp2, and then let's do it in blue again. All right, is it yp2? Yes. Okay, let's run this and see what this looks like. All right, so you can see here, so let's put these two figures next to each other. So this is the first set of data, and you can see this is the best fit least squares line, best fit line. And for this set of data, and this is the second order polynomial fit, which is the least squares fit that goes through this data point. You can see here that for the first case, it's not necessarily for the line to go through the data points, but it is the best fit line. And you can see here for the second, it can go through the line, the points. It can, but it's not necessarily to go through these data points. All right, so this is it for how to get the best fit least square curve that best fits your data points, and how to pick the model and how to implement this in MATLAB, and what are the right commands you need to use in MATLAB to implement this. I'm going to, as usual, include the link of the GitHub code, GitHub link, sorry, for the code that I used here in this video. If you have another way to do this, please add your comment in the comment section. Thank you very much, and I'll see you in the next video. Thank you.